Let us now discuss about differential equations that are exact. The differential equation m of xy dx plus n of xy dy equal to 0 is an exact equation if there exists a function f such that the differential of f is equal to m of xy dx plus n of xy dy. For example, we're given the equation 2x y cubed plus cosine x dx plus 3x squared y squared dy equal to 0. If the above equation is exact, that means that there exists a function f such that the differential of f is equal to 2xy cubed plus cosine x quantity dx plus 3x squared y squared dy. So we claim that the function f that we are looking for is x squared y cubed plus sine of x. So to prove our claim, we get the differential of f. We know that the differential of f is equal to the partial of f with respect to x dx plus the partial of f with respect to y dy. So for the given function f, we get the partial of f with respect to x, and that is equal to 2x y cubed plus cosine x. Our partial of f with respect to y on the other hand will be equal to x squared times the derivative of y cubed, which is 3y squared, and sine x being a pure function of x is treated as a constant, so its partial derivative with respect to y is 0. So we write the differential of f as 2xy cubed plus cosine x quantity dx plus 3x squared y squared dy. So hence, the given equation is exact because we were able to show the existence of a function f whose differential is exactly equal to the given differential equation. But at this point, the question that begs an answer is, when is an equation exact? Okay, how do we know that m of xy dx plus n of xy dy is equal to 0? So we need to find a condition for us to say that a given differential equation is exact. We start by considering the equation m of xy dx plus n of xy dy equal to 0. It is a differential equation of order 1 given in its standard form. First, let us assume that equation 1 is exact. Alright? So, from the definition of an exact equation, this means that there is a function f such that the differential of f is equal to m of xy dx plus n of xy dy equal to 0. And when we were discussing about partial differentiation, more particularly the differential of a function of two variables, we know that the partial derivative of the function f with respect to x is equal to the coefficient of dx, which is m of xy. And also, the partial of f with respect to y is equal to the coefficient of dy, which is n of xy. For brevity, we can just write this as m and the other one as n. Okay. For equation 2, let us take the partial derivative of the partial of f with respect to x, now with respect to y. So we take the partial derivative of 2 with respect to y and of 3 with respect to x. So the partial of f with respect to x, we take its partial again, but now with respect to y. That will give us partial of m with respect to y. For 3, we take the second partial, but now with respect to x. So that is equivalent to partial of n with respect to x. But we know that the order of the second partial of f with respect to x and with respect to y has no bearing. We know that the second partial of f with respect to y with respect to x is the same as the second partial of f with respect to x and with respect to y. So this means that partial of m with respect to y is equal to the partial of n with respect to x. So what we have just established is a necessary condition for the given equation, which is equation 1, to be exact. That is, when equation 1 is exact, then the partial of m with respect to y must equal to the partial of n with respect to x. What we are going to show in the next slide is that if the condition partial of m with respect to y is equal to partial of n with respect to x, then the given equation is exact. What we have shown here is that if equation 1 is exact, it follows that the partial of m with respect to y is equal to the partial of n with respect to x. But what we want to show is that if this condition is satisfied for the given equation, then the given equation is an exact equation. So we're still dealing with the same equation, but now we will assume that partial of m with respect to y is equal to the partial of n with respect to x. we will assume that the partial of m with respect to y is equal to the partial of n with respect to x, and we will prove that the given equation is exact. So let us start with a function phi. So we define a function phi of xy such that the partial of phi with respect to x is equal to m, right? How do we obtain this function phi? By simply getting the partial integral of mxy dx with respect to x. And that is how we can determine the function phi. Alright? So, our partial of phi with respect to x is equal to m. Now, we take the second partial of phi with respect to y. So, the partial of m with respect to y. And we know that by our assumption, partial of m with respect to y is equal to the partial of n with respect to x, which is also equal to the second partial of phi with respect to, we can interchange the order, now partial of x with respect to y. So let us now isolate this part. If we are to integrate the second partial of p with respect to x with respect to y, what do we get? We'll be getting the partial of phi with respect to y equal to n. Alright? If we are to take the partial integral of the second partial of phi with respect to x with respect to y, we'll be getting the function n plus some function g prime of y. Alright? Because we are taking the partial integral with respect to x. So, the inverse process of that is partial differentiation. Alright? So, the partial differentiation with respect to x makes a pure function of y equal to 0. So, taking the partial integral of the second partial of p with respect to x with respect to y will give us the function n plus some function, a pure function of y. Alright? Now, we define a function f or the function f as follows. F of xy is equal to phi of xy minus some function g of y. We then take the differential of f. Taking the differential of f means taking the partial derivative of phi of xy minus gy with respect to x dx plus the partial of phi of xy minus gy with respect to y dy. Alright? So we have phi of f equal to, we'll be getting here the partial of phi with respect to x dx. Alright? The partial derivative of gy with respect to x will be 0. Plus, we now go to the partial of f with respect to y. So that will give us the partial of phi with respect to y minus the partial derivative of a pure function of gy will give us g prime of y, everything dy. Now, partial of phi with respect to x is equal to m. So we write here m of xy dx plus the partial of phi with respect to y is n of xy. So let me just rewrite this simply as m. Okay, m dx plus the partial of phi with respect to y dy is none other than g, or n. That will be n plus g prime of y dy. So we have the differential of f equal to m dx plus, okay, I'm sorry, this should be, there is a missing term here, okay, minus g prime of y everything dy. Alright, so see that g prime of y will cancel, and it results to the differential of f equal to m dx plus n dy. So at this point, we have already shown that for the given equation, m dx plus n dy equal to 0, where the partial of m with respect to y is equal to the partial of n with respect to x, we were able to get a function f whose differential is equal to the given differential equation. Okay, so to wrap it up, no, we state the following theorem. If m, n, partial of m with respect to y, and partial of n with respect to x are all continuous functions of x and y, then a necessary and sufficient condition that the equation m dx plus n dy equal to 0 be an exact equation is that the partial of m with respect to y is equal to partial of n with respect to x. So, to find out whether an equation is exact or not is to simply get the partial of m with respect to y. Now, m is the coefficient of the x. Take its partial derivative with respect to y, and if it equals the partial of n, the coefficient of dy with respect to x, then the given equation is exact.